for your kind introduction, and it is my great pleasure to be back to Seoul. Is it still within the boundary of Seoul? Oh, outside. Yeah. Oh, yeah. And this is probably my 5th or 6th visit to Korea. It started about exactly 20 years ago. My first visit to Korea was about 20 years ago when I spent a month here, including Seoul and several other places. And it is always a pleasure to be back to Korea and see many senior people and also young people who are actively working on mathematics. And each time I'm glad to see their quick development and impressive level of research now going on in Korea. And to be honest, this is my first time in KIAS. I've never been here, and I'm impressed by this very, very nice campus. You don't have undergraduate students, probably only graduate. Oh, no student at all, zero. All right, okay. Anyway, I'm very glad to be here. So the title of my talk is Mathematical Analysis, as announced, of a 3D model of cellular electrophysiology. And this is joint work with Yoichiro Mori, who is in the University of Minnesota and who is now a mathematician, but he is also a medical doctor. He graduated the medical school of our university with a top score, and then he moved to Courant Institute and received a PhD there. And then after that, he moved to University of British Columbia, and now he's in Minnesota. And actually, I'm not really a specialist in electrophysiology, and I'm still learning a lot from him. This is his really special field, but also he's a mathematician. Okay, here's the outline of my talk. So I will first explain the background of this cellular electrophysiology, as I suppose that the majority of the audience here are mathematicians, and therefore I have to explain some basics which I learned just a few years ago. And then I will compare the 1D model versus 3D model. 3D model is the main focus of my lecture today. And then there's some mathematical principles that helps the analysis, which we call quasi-positivity principle. And this allows us to give uniform L-infinity bound on solutions, and etc. So let me start with the introduction. Okay, let me go on. So, this is just a schematic picture of what is called the neuronal axon. And we have in our body, I don't remember the number, but hundreds of millions of them within our body, you know, in the brain, in the heart, in many, many places, all over. And as many people here also know, I suppose, if some stimulus comes here, then this information is transmitted along this long part of the cell, which is called axon, and the short one is just less than 1 millimeter, but the long one in our body is more than 1 meter long. And in the case of dinosaurs, of course, it's much, much longer. And this axon acts as a wire along which electrical signals travel, like this. And it is known that the shape of this electronic signal is always the same. It is a kind of digital digital information. So each unit always in the same shape. And here the signal means that it is a progressive change in the membrane potential. What is membrane potential? I will explain it now. Okay, but here is a typical shape of the electrical signal that travels along this axon. It is something like this. And this is the membrane potential. What is it? Membrane potential is the difference between the inner potential and outer potential. And here's a cell membrane. And cell membrane acts something like a condenser. And there is a difference, there is a gap between the electric potential outside of the cell and inside. And so there is some discontinuity in some sense. And this discontinuity, VI minus VE, is called the membrane potential. In Japanese, we write it this way. And this is what propagates along the axon, and this transmits the information from this part to this part, and there's a long chain of this. And what creates this membrane potential? By some other mechanism, the calcium ion has a bigger density, a larger density inside the cell and smaller density outside of the cell. On the contrary, this is sodium, Na plus. This iron has larger density outside of the cell because of some mechanism. Then there are what is called ion channel. And ion channel is a kind of a window, a kind of a slit that allows exclusively some ions. For example, K channel, if it opens, allows only a gallium ion to penetrate through the membrane. So these channels are little holes, in some sense, gates along the membrane. And if it opens gallium ion, since it has larger density, it goes out. And if Na channel opens somewhere, then since Na ions have larger density outside of the cell, some of them enters. Of course, it is not a unilateral motion, it goes back and forth, but statistically, more Na ions comes into the cell. So, what is the result? If gallium channel opens, then more positive ions go out, which result in negative potential inside, because in the interior it loses positive ions. So this results in negative membrane potential. And if Na channel opens, positive. Negative or positive, it is only in relative terms. Already in the normal situation, there is a difference between the interior part and exterior part. So the in the natural situation, membrane potential is already negative. But if K channel is open, then it makes the membrane potential further negative. And if Na channel is opened, then it moves, it changes the membrane potential in the positive direction. This is what these negative and positive mean. So one can change the membrane potential by controlling the relative number of open Na and K channels. This is how it works. So this is again another schematic picture of these channels, and there's a gate. And if it opens, and if it is a K channel, it let exclusively only calcium ion to go through, and it blocks every other ions. And the same for Na channels. And this is called channel gating. And this is the important part. Some channels open or close in response to membrane voltage. And if it opens or closes, then it also affects the membrane voltage. So there's a mutual feedback. So it is something like that. So membrane voltage influences on the channel gating, and channel gating results in the change of membrane potential. So there's this kind of feedback. And there's also some gating is slow and other gating is fast. This also makes the dynamics of this potential change more complicated. And this is just a schematic picture, but what is explained here, this is taken from a book of Kina and Sneed. So if this was the, so I explained this kinetics, but if you put it in this spatially long place, long domain, then it could happen that this kind of dynamical change occurs progressively, and the change of the membrane potential moves. It changes the position. So you may have a traveling wave. And this explains the transmission of neural signal. And this is well explained in the book of Kina and Sneed, Mathematical Physiology, which appeared in Springer in 1998. And the famous model is this Hodgkin-Huxley model. This is a bit simplified. And they proposed this theory, which says that this electrical signal, which has always the same shape, mysteriously, it's kind of a digital signal, is created just by diffusion, reaction. This is a kind of reaction diffusion system. And they proposed this, and some people believed that, and some people didn't accept it. But later, they received Nobel Prize in 1963 because of this theory. At that time, this channel gating, the existence of ion channels, were not known. And they just found out these parameters from just experiments. So the detailed structure of the cell, particularly the existence of channels, ion channels, they did not know it, but they discovered that if you put these parameters, which is subject to this kind of dynamics, then they can explain everything. So with from the phenomenological consideration, with careful experiments, they arrived at this system. But these three parameters, and N and H, now they can be explained very well using this channel gating. So this is the background. But if you look at this equation, it is just one-dimensional diffusion equation. And this is what is called the 1D model. And this electrical potential, if you have a, for example, high peak, it diffuses because some charges escape, and it is diffused. So it is normal to put this diffusion term here, and this system is well inconsistent with a real experiment. If you do numerical computation based on this system, you have a very good match with a real experiment on the axon. But what if we take into the account the 3D structure of the cell, because the axon is not a single wire, but it has three-dimensional structure. So what happens if we take into account? So this is the cell. So axon, we are not just talking about axon, long axon, but short one. For example, the heart consists of many little cells, which also have this function. And it's a very large system of such cells, the heart particularly. So this is the motivation of our mathematical study of some models. And let me explain in more details. So once again, this is a Hodgkin-Huxley model, which I mentioned. And there is also a simplified version of, which is called Nagma Model. So you can derive Nagma Model from Hodgkin-Huxley model. However, Nagma Model also arises in some other contexts, more physical contexts, in physics, for example. So not necessarily only in cellular physiology. So Nagma Model is not just a simplified version of Hodgkin-Huxley model. It covers a wider range of science. But in this context, at least, this is a simplified version. And you have one diffusion equation here, and the rest is ODE. The rest is ODE because they are related to the channel gating, and the position of the channels don't move, of course, and they don't affect directly. There is no mutual interaction between different channels except through the electricity. So this is the assumption. So you have, except for U, which is the voltage, the rest is ODE. Now, if we consider a 3D model, then the situation changes a little. But in order to find out what is the right term instead of this one-dimensional Laplacian, we have to look at the cell itself. So this is a three-dimensional cell, and the surface, cell membrane is a two-dimensional surface, which I call gamma. This is a cell membrane. Then you have this kind of equation. So we assume that there is no charge inside and outside, and all the charges are on the surface. Then you have if VI and VE denote the Coulomb potential inside and outside of the cell, they satisfy these harmonic. They are harmonic functions, and then they satisfy this equation. This is the continuity of electric field, and this is sigma is related to the conductivity, ratio of conductivity between inside and outside, and V is the membrane potential, VI minus VE, which is defined only on gamma. So VI is defined inside of gamma, VE is defined outside of gamma, and the boundary value of these two functions are not the same in general, and this difference is called the membrane potential. This is V. And V sub E of x goes to 0 as x tends to infinity. So infinity has a value 0, potential 0. So this is the assumption. Then what happens is that these four equations and condition, asymptotics at infinity, this is to determine VI and VE from V. So V is what we have, what we want to know, as a matter of fact. And later we will work only on the surface gamma. So the function we have to look at is V. But from these four conditions, you can determine VI and VE uniquely. You can easily show that these conditions determine VI and VE uniquely from V. Once it is determined, then this normal derivative is automatically determined. Therefore, VI, dVi dN, this is the normal derivative of VI, is determined directly from V. And then you have evolution equation for V and W. W is another parameter which appeared also in the previous Hodgkin, Huxley, and his Nagma model. And then, by the way, I didn't remember how long is the lecture time.
40 minutes.
40 minutes. So okay, let me go quickly then. And then I define lambda to be a mapping from V to dVi dN. As I said, VI and VE are determined uniquely from V, so you have this map. And this is closely related to what people call Dirichlet-Neumann map, which is a non-local operator, but it is more complicated. It is not just simple Dirichlet-Neumann operator, because V is the difference between VI and VE, and therefore it is a little more complicated, but you can express lambda using a Dirichlet-Neumann operator. Anyway, it is a non-local operator. And okay, let me just go quickly. But then this is a closed equation on gamma. And in a special case where sigma equals 1, if the conductivity inside and outside are the same, it can be expressed by a simple integral formula. It's an integral operator, and anyway. But in general, if sigma is not equal to 1, it is more complicated. The expression is not so explicit. But it's a pseudo-differential operator, non-local. So what we obtain is an equation, non-local equation on gamma, pseudo-differential equation for this, and this is ODE. And Hodgkin, Huxley, and Fitz-Nagumo, both are written in this way. In the case of Hodgkin, Huxley, W is a 3 vector, and in the case of Fitz-Nagumo, W is a scalar. And the corresponding 3D cable model is the following. It has the same nonlinearity, but the principal term is different. And moreover, in the classical 1D cable model, it is defined on the real line. While in the 3D cable model, it is defined on the surface of a cylinder or whatever shape. And the goal is to prove well-posedness of the 3D model, existence local in time, uniqueness. As a matter of fact, it is not so difficult. And the more difficult part is to prove uniform bounds, elliptic bounds, and global existence. And this has been done. And then asymptotic smoothing. Okay, we don't have a smoothing here. There is no smoothing term in the ODE part. And therefore, W cannot be smoothed, cannot become smooth if the initial data, for example, W is a discontinuous function or just a continuous function. It cannot become smooth immediately because this is just ODE. Because of that, in the V equation, you have smoothing term, but however, since W is not smooth immediately, the smoothing is somewhat limited. The same here. But if you look at the omega limit set, long time behavior, as t tends to infinity, you can show that everything becomes C infinity in the limit. But in finite time, W may remain as a discontinuous function or just a continuous function. There is no smoothing. So this is this, and anyway, we discuss this kind of things. And let me just go a little quickly. So I will probably just explain just the idea because I don't think I can go into the details. But what makes the analysis more difficult for this second equation is the following. For this equation, in the classical model, this is just a diffusion equation plus some nonlinearity. And if you just take the principal part, it is well known that this diffusion equation satisfies the maximum principle. However, in general, this second equation, this minus lambda, this operator, which has some similarity with the Laplacian in terms of positivity in the L2 sense and other things, it is a bit similar, although it is a first order equation. This is second order, this is first order, but apart from this difference, there's also some similarity. However, unfortunately, in general, no maximum principle holds, except when the shape of the cell is close to a sphere. So, in the case of Laplacian, if you have a smooth function, if you look at a semigroup generated by this Laplacian, then positive functions remain positive. And a naive way of explaining it is if you have a smooth function and then you apply Laplacian, then if it touches, if a non-negative function becomes zero somewhere here, then the Laplacian is non-negative. And because of that, it prevents the function from going further negative, so the positivity is preserved. However, if you do the same thing for lambda minus lambda, it is not the case, except when gamma is close to a sphere. So this is okay, but this is not okay. Particularly in the case of an infinite cylinder, this is very, very bad. Okay, this is, and this is just to explain why the positivity doesn't hold. Let me go quickly. So how, there is a criterion to see whether positivity of minus lambda holds or not for a given surface. This is a perfect sphere. Then you place electric Coulomb dipole perpendicular to gamma everywhere. Then look at the line of electric force and see how many times it crosses gamma. Only one here. Every line of electric force crosses gamma only one and come back to the other side of the dipole. But if you do the same thing for this ellipsoid, then it crosses 3 times, some of them. Then the positivity, minus lambda doesn't have positivity. This is a geometric criterion to see whether on a given surface, minus lambda is a positive operator or not. If it is a positive operator, then the maximum principle holds. So if you are working just on this kind of a perfect circle, then it is not too different from the classical Laplacian model. Okay, now let me just go very, very quickly. How did people prove the existence of time global solution for Fitts-Nagma model? This was done in late 1970s. It is a system of equations. If it is a single equation, it is very, very easy to prove, for example, for Allen-Kahn equation or KPP equation. If you start from some bounded initial data, it remains bounded. And if it remains bounded, then local existence theory shows that you can continue the solution globally in time. But the key point is the global bound in L infinity. And it was not that easy for a system. And in the case of Fitts-Nagma equation, this was done only in late 1970s by using what is called the invariant rectangle. And it is a simple idea. If you look at this ODE without this Laplacian term, you can show that if you place a rectangle in the phase plane, this rectangle is positively invariant, and all the vector fields on the boundary of this rectangle point inward. All the orbits of ODE enters. Then you apply the maximum principle to show that it is also positively invariant in the presence of diffusion because of the maximum principle. And this is how the uniform boundedness was proved in late 1970s, and this was done by Mimura in 1976 and Ralph Smoller in 1978. But this argument does not work for the 3D model because you don't have maximum principle. And then it was the bottleneck for many people who wanted to study this, but we found a very, very simple idea, extremely simple, to overcome this difficulty. And so this is the following. Okay, the positive operator is what I explained, that Laplacian is a positive operator in that sense. And quasi-positivity is the following. An operator is called quasi-positive if it is given, if it is a sum of a positive operator and a bounded operator. And this expression may not be unique, but there is you can find the infimum of this, the norm of this bounded operator, norm in the continuous space of continuous function on a given compact surface K. This is called the non-positivity index. If the non-positivity index is 0, it means that L is positive. And if it is positive, then it is not. But what is important is that B is bounded, and P may be unbounded, like Laplacian, or minus lambda, but unbounded part is in the positive direction, and in the negative direction, bad thing doesn't happen because B is bounded. So it can pull below, but only in finite strength. This helps. And let me skip the details, but using this, we were able to, okay, let me skip this. We were able to show the global existence for Fitz-Nagmo and Hodgkin-Huxley. For Hodgkin-Huxley, we needed a little more work, but we were able to use what we call modified invariant rectangle method. Because this, you can show in the case of Fitz-Nagmo, this ODE, this vector field, points inward very, very strongly, superlinearly. And the lambda has a positive part and a bounded part which may want to go outward. Lambda is decomposed into positive part plus bounded operator, which may not be positive. But this is a linear only, linearly strong. So if you have a superlinear vector field which points inward, then you have a invariant rectangle. It is not the same in the case of Hodgkin-Huxley, because in the case of Hodgkin-Huxley, this part is only Lipschitz continuous. Then you need a little more dedicated analysis to prove the invariance of this rectangle in the case of Hodgkin-Huxley. But for Fitz-Nagmo, it's easier. So using this, we were able to show the global existence in L infinity. And finally, we wanted to study long-time asymptotic smoothing, because smoothing does not occur immediately because the second equation is just ODE. But we were able to show that you can do bootstrap argument in the omega limit set. And therefore, you can show that omega limit set consists of C infinity functions. I'm sorry, I don't have time to explain the details. But finally, the more difficult case is infinite cylinder. So far, I only explained the situation of compact surface. Of course, every cell is compact. It's a finite length, finite size. But if you want to study traveling waves along a long axon, mathematically it is better to consider infinite cylinder just to capture the essence of the phenomenon, mathematical idealization. This is indeed necessary, because everybody who walks on the traveling wave walks on an infinite domain. The same. But in this case, non-positivity index is infinite. So our principle does not hold. Then we needed we needed to use Fourier decomposition along the Fourier decomposition in the theta direction and the Fourier transformation in the x direction. And we were able to prove something using modified estimates of modified Bessel functions, which appears in the Fourier operator here of each lambda n. Okay, let me just finish. This is the shape of this Fourier coefficient. In the case of Laplace, it is parabola. In the case of minus lambda, it is asymptotic to two lines, because it's a first order. But this part is very, very similar. Okay, I think I should finish this, and those who are interested, I can give you more. And what is mostly interesting currently is epileptic coupling, interaction between the parallel cylinder. This can be studied using our model. Okay, I think I should stop here. Thank you very much.